You are joining us here for Astronomy Night in Canada. It is Monday night, so you know the drill at this point in time. Although there's going to be a slight change in things tonight. We're going to refer ourselves to Science Night in Canada. And the reason for that is that after our broadcast of York Universe, we have Western World's Marine Mammal Science tonight, a new podcast to check out, not to mention Science for the People. Don't worry, Quirks and Quarks will be back next week. Okay, so there's a lot of good stuff coming, even if the lineup is a little bit different. York Universe broadcasts every Monday night at 9 p.m. local Toronto time, which of course is Tuesday morning, 2 a.m. Universal Coordinated Time. Yes, we're still on standard time, although those days are coming to an end. Within 2 weeks, it'll be daylight saving time again. I guess that's a sure sign of spring in the air. The York Universe production works in concert with our online public viewing program run by the Observatory team. Hi there, team. And of course, not surprisingly, they run at the same time as us from 9 till 10 p.m. here local time. By all means, point your favorite web browser to observatory.info.yorku.ca and follow the links to OPV, online public viewing. Of course, you can reach us via YouTube as well, Alan I. Carswell OBS. Our broadcast is powered by and is in partnership with Astronomy.fm, the voice of astronomy. If you've got any questions or comments about past shows or suggestions for future shows, by all means, send us an email, observe@yorku.ca. You can always connect with us on Twitter or Instagram with the handle @York Observatory, and on Facebook, Alan I. Carswell OBS. All of our programs are free, but if you would like to make a donation, by all means, visit our website, observatory.info.yorku.ca, and hit the big friendly donate button there. We will be monitoring the chat room for questions. Unfortunately, it is cloudy out here. I don't think it's snowing at this point in time. So there will not be any live images from our 1 meter telescope. But nonetheless, the observatory team will be showing lots of past content, wonderful images from our 40, 60, and 100 centimeter telescopes. So tune them in, online public viewing at our website. So, how are our two intrepid co-hosts this evening? Sana?
I'm doing well. Yeah, everything's going pretty well for me right now. How about you?
You've caught up on all of that reading, have you? Well, it was reading week. I mean, you were supposed to catch up on all that reading.
I did a good amount of reading over reading week. I read a couple papers.
Very good. And you've been spending some time in the observatory as well?
Yes.
Yes. My dear wife, every time I tell her, guess who's on the observatory tonight? She just now automatically says, Sana. Yeah, okay.
It's nice to use the 60 centimeter again.
Well, no argument from me. The 1 meter is a nice instrument, but you know what? The 60 centimeter still has my heart. What can I say? Satish, the West Coast. Mild, no negative temperatures, no shoveling snow. I mean, what do you do with yourself? I mean, really?
Okay, so let me correct you here. We actually did have negative temperatures last week.
Ooh.
Like real, actual negative temperatures and snow in Vancouver, which is great stuff, I think. I don't know. And yet I was able to, not actually yet, of course, the skies were clear. So I think I did see Venus and Mars together, like close by.
Over
on the
west
horizon somewhere.
Yep. Mm-hmm.
Yes, exactly. So, and I double checked. I was like trying to make sure I'm looking at the right thing. And I guess I was correct. So, yeah.
Excellent. Yes. Oh, very good indeed. Very good indeed. Did you have to teach everybody about the number line? I mean, negative temperatures, they're just not used to that sort of arithmetic over there. I mean,
I don't think anybody's interested because people are sitting back home. So that's fine.
Well, that I can believe. Why learn about negative numbers when it only happens once a winter? Fair
I was thinking probably once in a millennia or something. But
I think it's a little more frequent than that, but nonetheless. Okay, folks, I have a question for both of you, and you can think carefully about the answer, and we'll chat about the answer between This Week in Space and Astronomy History and our news items. I want to hear from both of you when you began to think about becoming an astronomer. studying astronomy. Okay, so there's your homework while we're wandering through this week in space and astronomy history. When did you think about becoming an astronomer, studying astronomy? All right. On that note, though, let me lead us into this week in space and astronomy history. Want to head back to 1979, March of 1979, in and around March 4, 5, 6, 7, 8, the first week or so of March, and you'll see why in just a moment. This was the Voyager 1 flyby of the planet Jupiter. Now, Voyager 1, I mean, everybody knows about Voyager 1. It was launched back in September 5, 1977. It was part of the grand tour of the outer solar system. It was a NASA-conceived mission where Voyager 1 and Voyager 2 would slip by all of the major planets, Jupiter, Saturn, Uranus, and Neptune, the four gas giants of the outer solar system, taking advantage of an alignment that occurs about every 176 years, a bit of gravity assist, playing a little bit of planetary billiards. Voyagers would both utilize the larger planets for gravity assists, change their orbital trajectories without the expenditure of a lot of fuel, and move on to their next targets. And Voyager 1, of course, visited both Jupiter and Saturn, whereas Voyager 2 went on to visit Uranus and Neptune as well. So Voyager 1 was the one that led the way. Even though it wasn't launched first, it led the way as far as the encounters with Jupiter and Saturn were concerned. And just out of interest, Voyager 1 is currently still transmitting data to us. It is 156 astronomical units from the sun. That's nearly 4 times the average distance that Pluto is from the sun. So not half bad. At any rate, let's just stay in and around March of 1979. March, when we think back to that time, there was lots and lots of excitement that was taking place. On or about March 5, well, not on or about, on March 5, we had the closest approach of Voyager 1 to the planet Jupiter. It came within about 349,000 kilometers. Not particularly close by close encounter standards, but as I said, they were utilizing Jupiter to get onto Saturn and Titan and so on. So it didn't need to get too close. And of course, the closer you get to Jupiter, the harsher is the radiation environment. So they were playing, protection a little bit, if you will. So closest approach, March 5. But the day before, there were images taken and there was the detection of the ring system of Jupiter. Everybody knows, of course, the ring system around Saturn. It looks beautiful. You see it in small telescopes. We found the ring system around Uranus in 1977, the Kuiper Airborne Observatory and occultation measurements. So there was a suspicion that perhaps rings were far more common than we had been led to believe. And sure enough, careful observation of the imagery that was coming back from Voyager was suggesting that there was a ring system around Jupiter as well. Third ring system in the solar system. Now, by comparison with Saturn's ring system and even the Uranian ring system, the Jovian ring system is really very, very small. It is quite diffuse. In fact, the term that is often used is gossamer in nature, so it's a really thin veil. It extends from around about 90-odd thousand kilometers from Jupiter's center out to about 225,000 kilometers. So it's got a pretty broad sheet, shall we say, well over 130,000 kilometers from inner edge to outer edge. Generally speaking, it's only a few hundred kilometers to perhaps a few thousand kilometers in thickness. It's very dusty. It's generated by impacts on the inner satellites of Jupiter. Remember, Jupiter's got like 80 satellites. Well, the 4 innermost satellites seem to have been pounded mercilessly over the years, millennia. And of course, given Jupiter's gravity, that's not much of a surprise. And these 4 satellites keep discharging dust and gravel. And that is what seems to make up the ring system. It's got sort of 3 parts, a halo, a middle, and then this gossamer section. The main section, as the name suggests, is the thickest part. But nonetheless, when all is said and done, you've really got to look hard, even in the Voyager images, to see the ring system. But nonetheless, it was found in images March 4th, in and around closest approach on March 5 of 1979. But the fun wasn't over just yet. 3 days later, March 8th, navigation images were being taken of Io. And lo and behold, Linda Morabito managed to detect volcanic plumes. Now, Linda, by the way, she was born in Vancouver, British Columbia. I did not know that until I was actually researching this story. So, big shout out to Linda. But she was on the engineering team and was doing navigation of the ring system, not the ring system, the Jovian system in the background stars, and she saw a plume which was completely unexpected rising out of Io. And this was really a big, big discovery. In fact, over 150 active volcanoes are now known to exist on Jupiter. Come on, Paul. On Io, we speculate that perhaps there are as many as 400 active volcanoes on Io. We haven't been able to detect them all at this point in time. And of course, they are spewing material into the Io orbit around Jupiter. And that, of course, is interacting with the Jovian magnetic field, and it's generating auroral activity. I mean, it's a really complex system, all because of this volcanism. The surface of Io is very young because of the tidal heating, which is what is generating the volcanism, which of course is resurfacing Io on a regular basis. So all of this was happening in and around closest approach. Most of the really exciting stuff for the Jovian encounter of Voyager 1 occurred sort of March 4th to March 10th or thereabouts. Although, of course, Voyager was observing Jupiter for the preceding month and the ensuing month. So it was about a 2-month suite of observations, but all the excitement was in and around March 5. So ring systems, volcanic activity around Io, you name it, Voyager 1 gave us a lot of really exciting science for its first encounter with the largest planet in our solar system, March 1979.
I'm tempted to ask, who is Pluto?
Who is Pluto?
You said in the beginning, it went past Pluto, as in twice the time.
Oh, well, yeah, I was just trying to give a scale reference that Voyager is over 160 astronomical units. On average, Pluto is 40 astronomical units from the sun. And of course, most people who are listening to us grew up with Pluto being a planet, right? So the edge of the planetary system was 40 AU. So I was just giving a scale there. Pluto is always considered to be a long way out. Well, Voyager 1, 44 years and counting, 160 astronomical units. So Pluto was just being used as a scale, a milestone.
Well, actually, I was literally being sarcastic about the status of Pluto, nothing else. And of course, not at you. I was just like trying to incite the conversation about Pluto, which I always do. So that's pretty much it.
I'm going to get a buzzer and
excuse me for that.
Either that or you and Ariella are in cahoots, one of the two. Anything is possible. But yeah, the Voyager.
You would laugh, so.
I'm sorry. I took you far too seriously. I do apologize. The Voyager probes, though, really exciting stuff there. When you think about, what we have done in the ensuing decades, when you go back to 1977, the Voyager computer systems, basically your wristwatch has more computing power than the Voyager spacecraft. Yet here we are 44 years later after these terrific encounters with Jupiter and Saturn, and then Voyager 2, Uranus and Neptune. It just really, to me, is amazingly great science and technology that went into these missions.
And even now, I find with all of the amazing, just like looking at pretty pictures of these planets, still some of like my favorite pictures still come from the Voyager probes. Even with the amazing like high resolution stuff from Juno and Cassini, it's just still fantastic.
I'll agree with that. I mean, these probes did the encounters for the first time, just about. I mean, I know Pioneers 10 and 11 had gone past, well, Pioneer 10 had gone past Jupiter before Voyager 1, but nonetheless, the whole exploits of Voyager from Jupiter to Saturn, around Titan onto Neptune, Uranus and Neptune, these were big first encounters, and those images were really mind-blowing. There is one other little point that I forgot to mention. The fact that Io was so volcanic was actually predicted. Peel et al. Actually made the prediction that Io would be, because of tidal heating, volcanically active. Now, I don't think they really expected it to be as volcanically active as it is, but they actually did publish peer-reviewed article several months before the Voyager encounter suggesting that there would be volcanism on Io. That was Peel et al. And they were dead right. One of the really great predictions in modern planetary astronomy. Okay. Oh, sorry. Yes?
No, I was saying, so I could usually wonder at the amount of precision that cameras at that time would have, and how they actually carried it into cold dark space for so long, or like went on for so long. So, but I guess that's a big thing to talk about. So just shut up.
Yeah, well, you're not wrong. You're not wrong. As I say, the technology from the 70s, let us just say it is very robust.
Yes. Yeah.
Sana, bring us a little closer to home.
All right. So going to March 3rd, 1969, yet another mission that was amazing but ran on computers where our phones are more powerful than the computers these missions used in the 60s, which is the anniversary of the Apollo 9 launch. Apollo 9 was the third crewed flight of the Apollo missions, and while most of them were missions to the moon, there were 2 Earth-orbiting missions that tested different components of the spacecraft that Apollo astronauts would need to use when they actually went to the moon. The first one was Apollo 7, and then later Apollo 9. They were made up of the spacecraft to take people to the moon were made up of 2 different components. You have the command and service module, and then the lunar module, which the command service module was mainly responsible for bringing astronauts to the moon, and then the lunar module was what would take 2 of the 3 astronauts on board to the surface of the moon and then back again. And before NASA was ready to put people in these things and send them to go land on the moon, they needed to test the different components of the spacecraft. And most of these tests were done in orbit around the Earth because there was just no need to go to the moon to do those. A couple of the other missions, Apollo 8 and Apollo 10, did go to the moon and did test some of the components there. But a bulk of the testing for the command module and the lunar module were done in lunar orbit. Apollo 7 tested the command module, and then Apollo 9 tested the lunar module and the command module. So the way that the lunar module mainly acted as a spacecraft on its own, and then also the way that the lunar and command modules could interact and work together to create one spacecraft when they were docked. Mainly the things that both Apollo 7 and Apollo 9, but also for some things only on Apollo 9 were tested, was they wanted to test things like the module systems and procedures, including how their engines worked, their navigation abilities, life support systems, and very importantly, their docking and undocking procedures, which would be critical to do the lunar landings, since the lunar module would have to detach from the command module and then later redock with it to bring astronauts back home. Like all of the Apollo missions, the crew of Apollo 9 consisted of 3 astronauts. In this case, it was Commander Jim McDivitt, Command Module Pilot David Scott, and Lunar Module Pilot Russell Schweikart. The 3 of them spent 10 days in Earth orbit, which is about the time that one of the Apollo missions would have lasted, or one of the early Apollo missions at least. The command module, this was still the time when NASA was giving command module and lunar module fun nicknames. They were always given nicknames, but this was back before they were too worried about being professional for everyone. So the command module was named Gumdrop and the lunar module was named Spider, since that's what each of the modules kind of looked like. And like I mentioned before, one of the most important mission goals for Apollo 9 was testing the rendezvous and docking procedures between the lunar and command modules. The command module had already been tested pretty well on both Apollo 7 and Apollo 8. So their focus on this mission was really the lunar module itself, how it can act as a spacecraft by itself, can it support life, and can it successfully reconnect to the command module to bring astronauts back home after going to the surface of the moon. They did most of this testing within the first 5 days of the mission, just because their logic is that if the mission needs to get cut short for any reason and we need to come home, they want to have as much testing and as much data as they possibly can on the spacecraft. So the first few days were really action-packed. One of the most important things that they did had to do with the lunar module docking and undocking. They ended up doing this twice. First was while the lunar module itself was still connected to the third stage of the launch vehicle, the Saturn V. And then the second time they did this was the lunar module itself flying as an independent spacecraft, which is the first time that had ever been done. The lunar module had never been flown before. So that was a pretty kind of make or break moment for the lunar module, is can this thing work well enough to support life for a few days? After undocking for the second time, when the lunar module was working on its own without the support of the third stage, the crew who was in the lunar module, Jim McDivitt and Russell Schweikart, tested its ascent and descent system by firing the thrusters to change its orbit, which would be necessary to do when they were trying to land on the moon. And then when the two modules were docked again, the crew tested if the spacecraft could be maneuvered by a single engine. Primarily, the engine used for this is the command module engine, and that's how the spacecraft would be maneuvered when they were on their way to and from the moon. However, they also did test out how the lunar module's descent engine could manipulate the two spacecraft and drive it together. And that would prove to be very critical for the Apollo 13 mission, where they relied on part of the lunar module's engine to survive. Finally, one of the other important things they did was a spacewalk that involved David Scott and Russell Schweikart to basically just practice an emergency rescue procedure for astronauts in the lunar module. This was just in the event that the lunar module and command modules couldn't reconnect properly. They would have the astronauts in the lunar module exit the hatch, climb outside the spacecraft, and back into the hatch on the command module. So like I said, all the major tests were done in the first few days of the mission. And after that, the remaining days were spent doing some other more minor tests, but it was a lot done at a much slower pace, and the astronauts had lots of time for Earth observations looking out the windows. So that is I don't really know, over 50 years since the Apollo 9 launch.
53, in fact. But yeah, I still remember the Apollo 9 mission very fondly. And when I was sort of reading the newspaper and listening to the reports, remember no internet back then, it was always such sort of like a letdown for the astronauts, because of course we knew that we were getting really close to the moon landing. Apollo 10 was going to the moon, Apollo 11 was going to the moon, Apollo 8 had just come from the moon, and here Apollo 9 was stuck in Earth orbit. And all I could think about was the astronauts must have felt cheated. Of course they didn't feel cheated, but that was what my reaction was to the Apollo 9 mission. Let's get on with it, people. Let's get to the moon. But unless NASA had this very deliberate plan, as you explained in great detail there, Sana. They wanted to test this, that, and the other out thoroughly before they committed themselves to doing all of that 350,000 kilometers away. But I always felt for the astronauts that they were just stuck going around the Earth. Anyway.
I read a book that talked a lot about the Apollo missions. And one of the things that they had mentioned is for Apollo 10, which was like the dress rehearsal for Apollo 11, where the lunar module went and did like a fake landing. They didn't actually land. They just kind of lowered their altitude and then came back. As everyone was kind of joking, but not really joking, about how if the astronauts had enough fuel, they would have actually just done the landing.
That's right. They got within 10 kilometers of the lunar surface.
Mm-hmm.
So again, feeling cheated. But the slow and methodical approach, you really can't fault NASA for their their thoroughness. But gosh, just imagine being one of those astronauts of Apollo 9 or Apollo 10, knowing that all future Apollo missions were going to do the real thing. Yeah, you got to be patient to be an astronaut. They did a good job. Shatish, you've got a few people you wish to shout out to.
Yes, sir. I'm hoping that's okay because they're all like biggies, and it's pretty surprising, or rather, pretty coincidental that all of them were born on the same day. Of course, centuries, not
Go
centuries
for it.
apart, but okay. Well, that was the disclaimer. So, birthday shout out, my style. The Nobel laureates born on February the 28th and relating to physics and astronomy or something in science. The first one is Linus Pauling, not Pauly, Pauling. He was born in 1901, and officially he's listed as everything else but a physicist. Nevertheless, he's quite rightly also known as one of the greatest scientists of all times. Wouldn't get into the detail. His work on electronegativities of elements and X-ray crystallography are rather relevant or readily relevant to physics. And then he was also one of the only 4 people in the world to receive more than one Nobel Prize, both being unshared or individually claimed. There was one for chemistry and the other one was for peace. And then he's also the only other person apart from Marie Curie to receive Nobel Prizes in different fields. He was also a close friend of the physicist Robert Oppenheimer, a fact which subtly highlights his contribution to the physics of materials, X-ray crystal diffraction, electron diffraction instrumentation, etc., during his time at Caltech and UC Berkeley. As for the date of February 28th, there are others, the names we should certainly honor. So Daniel Shi Tsui, I hope I'm pronouncing it correctly. He shared the Nobel Prize in 1998 with Robert B. Laughlin and Horst L. Stürmer for discovering a form of quantum fluid with fractionally charged excitations. Pretty heavy in the name itself. Then we have Leon Cooper, who shared the Nobel Prize for Physics in 1972 for the BCS theory of superconductivity with John Bardeen and John Robert Schiffer. He's also well known for the Cooper pair and the BCM theory of synaptic plasticity. So material physicists will, of course, immediately recognize this. And then we also would like to give a shout out to Stephen Chu, who shared a Nobel Physics with Claude Cohen-Tanouji and William Daniel Phillips in 1997 for cooling and trapping of atoms with laser light. I'm sorry, I probably missed the years that they were born, but obviously they're all the 20th century. So happy birthday to all the Nobel laureates of the 20th century.
Wow, quite the collection there. Certainly for me, by far the one that I know the most about is Linus Pauling. Although the others I have recalled from my passing through physics history, but Linus Pauling was really one of those giants of the first part of the 20th century. And the Pauli exclusion principle. Chemistry was where you often think of Pauling, but his contributions, as you indicated, not the least of which is his interactions with Oppenheimer, certainly led to a lot of good physics being generated by him. Quite the titan of the early 20th century in physics.
Yes, and in fact, I'm looking at the years, like I said. So he was 1901, of course, and Daniel's Shi Tsui, he was born in 1939, Stephen Chu in 1948, and then Leon Cooper, missing it somewhere, was in 1930. So except for Linus Pauling, the rest of them are probably the same era or decade.
Pretty well. Yeah. Well, that's right. That's quite true. Pauling is the elder statesman, shall we say, of the group. Right. But how about that? To have so many Nobel laureates born on February 28th.
Precisely.
Yeah, quite the surprise. Okay, so moving from birthday shout-outs, another space probe of note. The European Space Agency's Rosetta spacecraft was launched March 2, 2004, so a little more recently in this regard. It was launched from French Guiana, and of course, the workhorse of the European Space Agency is the Ariane 5 rocket, and that was what was used to deliver Rosetta into its long-chasing orbit of the comet. The comet was Churyumov-Gerasimenko 67P, and it took Rosetta about 9.5 years to track this comet down. The aim of the exercise, of course, as the name suggests, Rosetta, of course, was that wonderful prehistoric stone that had a multiple language inscription on it, differing languages, Greek, Latin, I think Egyptian hieroglyphics, if memory serves, and everybody was hoping that the Rosetta spacecraft was going to be able to unlock a variety of secrets associated with cometary activity. The aim for the Rosetta intercept, which was in 2014, August of 2012, the aim of the exercise was for this spacecraft. Actually, I'm going to go back and say 2012 sounds wrong. I think it was 2014. My notes, I think, are incorrect. But at any rate, 2012 or 2014, the aim of the exercise was to put Rosetta into orbit around this comet just prior to its perihelion passage through the sun, or around the sun. And of course, in that way, Rosetta would have a ringside seat for the comet as it was becoming increasingly active. Most of a comet's life is spent out in the deep chill of the solar system, well clear of the solar furnace. It then sweeps in past perihelion. It gets heated furiously. It begins to discharge a tail. Lots and lots of action happens in the core, in the nucleus of the comet. And so the expectation, the hope for Rosetta was that it would witness all of these events and give us a much more precise insight into the cometary behavior. And of course, comets, as we all know, are the time capsules of the solar system. They formed back 4.5 billion years ago, have been largely unprocessed in that period of time. Yes, they get heated and cooled, but from the point of view of chemical differentiation and so on, not much has happened to them. So when they are discharging material, it really is releasing information about the earliest moments of our solar system. So Rosetta was hoped to be, that key, if you will, to unlock the secrets. Once it swung into orbit, it kept a sort of 10 to 30 kilometer separation from the comet. Lots of high-resolution imagery, obviously. There was something like a dozen instruments on board, the usual suite of cameras, UV and X-ray spectrographs, radio science equipment, and so on and so forth. All the good stuff. And it carried with it a little lander by the name of Philae. Philae was going to be deployed onto the surface of Comet Churyumov-Gerasimenko, and it did on November 12th of that year, and I'm quite sure it was 2014. And as a consequence of that landing, it wasn't quite the landing everybody had expected. They knew that the gravitational field of the comet was going to be very meager, and therefore they prepared, this is the European Space Agency, prepared for contingencies that would allow Philae to sort of, harpoon the surface. They had a little nitrogen gas cylinder on the top of Philae that would provide counter thrusts with respect to the motion of Philae as it was landing. And if all that failed, they had little drills on the ends of the feet of Philae that would immediately sort of core into the asteroid to try and grab a hold of the asteroid to stop Philae bouncing. Yeah, the European Space Agency went 0 for 3 on that. All mechanisms failed, and Philae bounced. And it bounced 3 times and skidded to a halt, unfortunately, at the base of a little cliff and deprived itself of sunlight and therefore solar energy. The batteries on Philae lasted for about 72 hours, which is what was expected. They gave back lots and lots of good data for the 9 instruments, but everybody had hoped that Philae would transmit for perhaps weeks to months. Didn't happen. Nonetheless, the Philae mission and the Rosetta mission are certainly classified as rip-roaring successes. Rosetta was finally soft-landed onto the comet September 30th of 2016, and that marked the official end of mission. So, the first time we went into orbit around a comet, the first time we landed on a comet. 3 cheers, a tip of the hat to Rosetta and Philae, launched back on March 2, 2004.
It's a moving target, and moving targets are always harder to sort of hit.
Absolutely. Absolutely. As I say, 9.5 years chasing it down. I think that's a pretty impressive feat. And for most of that time, of course, the spacecraft was in hibernation. It didn't have much to do while it was chasing the comet. But that means, of course, that the mission was, in its entirety over 12 years in length. So that's a pretty long time for a spacecraft. And the last 2 years of that were really quite frantic with all of the wonderful observations. Now, it was an excellent mission by the European Space Agency. There was also some public excitement as they were waking up Rosetta. If you look around on the internet, you'll find all sorts of snippets that basically says, wake up Rosetta. And I remember the observatory team here at York, led by Jen Zomederis, actually led us all in a chorus of wake up Rosetta. And that was in the January of 2014. I don't know whether Rosetta heard us, but she woke up, and that was great.
I'm tempted to almost call it like a second moon landing, because of the difficulty of the mission. Of course, it's not like it's as good as or as complicated as the moon landing. But I'm just impressed. Yeah.
It certainly was complicated, though, no question. As you said, a moving target, and the lack of gravitational field is what really messed around with Philae. I mean, they're lucky it didn't bounce back into orbit. So
it's also so much smaller than the moon.
Oh yes.
Yeah.
Like how hard it is to send something and have it actually orbit the moon or even hit the moon. It's like this thing is so much smaller and it's exponentially harder to find it.
That's exactly right. I think Comet CG was only sort of like 3 or 4 kilometers in size. It all looks a little bit like a rubber ducky. A couple of bulbous pieces stuck together there. But yeah, it's not very big. So as you say, Sana, you had to be very, very precise in your orbital dynamics. 9.5 years. And I don't know, it probably traveled 1 billion kilometers in that time, and it had to go into orbit around an object that was only a few kilometers in size. It really is a testament to good engineering, good celestial mechanics to be able to, find those sorts of objects and execute your orbital plans. Satish, speaking of space missions that had long lives, Pioneer 10.
Yes, sir. And I think I'll just be adding to all the comments that you've already made. So March 3, Pioneer 10, we're sort of celebrating the launch date or remembering the launch date. It was the first space probe to complete a mission to Jupiter, and also the first of 5 artificial objects to achieve the escape velocity needed to leave the solar system. And I think, Professor, as you mentioned earlier, Voyager probably was after this. I don't remember the dates, but I guess it caught up to Pioneer pretty quickly in terms of its speed.
Mm-hmm.
Yes. And then, so back to Pioneer 10, it was launched on March 3rd in 1973. Actually, 1972, by an Atlas Centaur expendable vehicle. It went past the asteroid belt in 1973 and began imaging Jupiter in November that year. So its closest approach to Jupiter happened in December of the same year at about 132,252 kilometers. And then the 258 kilogram heavy probe lost contact with us in 2003. That's a pretty long time to stay in touch. I mean, not that others aren't right now. And at a distance of 12 billion kilometers or 80 astronomical units. As of 2019, it was predicted to be as far as 122 astronomical units in the direction of the constellation Taurus. So while I've just mentioned like the technical details, all I can say is that it's been amazing with these missions and the 5 of them. they have made out of our solar system, probably. Not probably, actually they have. So.
Correct. Yeah, Pioneer 10 has left the solar system. It is beyond the nominal heliosheath. Of course, it wasn't active when it passed through that barrier. That's the big difference between the Voyager probes and the Pioneer probes. The Voyager probes were still active and were able to be transmitting data about their environment as they crossed the heliosheath. Unfortunately, the Pioneer probes were unable to have that length of life. But nonetheless, 30 years of transmitting data is nothing to be disappointed in. And the other reason that they won't catch the Voyager probes is the Voyager spacecraft picked up gravity assists from Jupiter and Saturn in the case of Voyager 1, Uranus and Neptune for the case of Voyager 2. Pioneer 10 went to Jupiter and then out. So it didn't have the opportunity to pick up extra energy from the outer planets. That's why it's only I say, 122 AU out compared to Voyager 1, which is 158.
Right.
Good effort, though, by the Pioneer probes, and the first images they had sent back of Jupiter, again, very impressive. Certainly far better than any ground-based observations of the time. Not nearly as good as the imagery we see today, but nonetheless, let's think back. 70s technology, not nearly as good as it is today, but those first images of Jupiter were pretty special, that's for sure. Sana, do you want to finish us off, please?
Yes. So this is yet another incredibly successful mission, but instead of looking at our solar system, it's looking at other solar systems. So that's the launch of the Kepler Space Telescope, which is either March 6th or March 7th, 2009, depending on if you look at the universal time or the local time from the launch site. I'm just going to say it's on March 6th. So Kepler was NASA's first exoplanet hunting telescope. It has tests now that it launched later, and many other NASA telescopes do look for exoplanets. But Kepler was kind of a dedicated telescope that looked specifically for exoplanets. This was in the early days of exoplanet observations where there hadn't been many detected and there weren't a great variety of them. So NASA launched Kepler, whose main priority was essentially to get statistics on exoplanets, determine if Earth-sized exoplanets were common, and to also confirm some existing exoplanet candidates. Kepler used the transit method, which is where you can detect the exoplanet based off of how the star's brightness changes when the planet crosses in front of the star from our point of view. Based on how much of this light is dimmed and how long it's dimmed for, how long it takes for the star to dim again, you can determine a bunch of properties about the planet, like its size, its orbital period, how far away it is from the star, and even some other interesting things like the temperature on the surface of the planet. Kepler was an incredibly revolutionary mission for the field of exoplanets for quite a few reasons. So first of all is that Kepler could monitor thousands of stars simultaneously. It monitored about 170,000 stars at a time, so it was able to get large numbers of statistics on exoplanets and exoplanet candidates and find a ton of them just because how many stars it was observing. And one of the important things that Kepler discovered because of that is that on average, every star has at least one planet. The second thing that made Kepler a pretty revolutionary mission is just because of how precise it was. It's able to determine the change in brightness of stars down to a fraction of a percent, which is necessary for finding exoplanets because stars only block a pretty tiny amount of light from their host stars. So before Kepler, most stars that were found were really big Jupiter-sized planets that orbited close to the star, so they blocked a decent amount of light from the planet. But because of Kepler's precision, it was able to expand the kinds of exoplanets that were found. So it allowed for the discovery of much smaller, more Earth-sized planets that orbited at larger distances away from the stars. As with most NASA missions, Kepler far outlived its original mission design. It was supposed to last for only about a year, but ended up lasting 9 years, and even survived a partial failure where 2 of its 4 reaction wheels failed. So NASA ended up coming up with this new modified K2 mission where it actually used pressure from the solar wind to keep it pointing in a certain direction, which I think is pretty cool. I didn't really ever think that was something you could do, but that's awesome. And so after 9 years of operations, the mission came to an end on November 15th, 2018, when it ran out of fuel. And something that's pretty interesting about this is that's actually the 388th anniversary of the death of Johannes Kepler, who the telescope is named after. So overall, Kepler answered a lot of questions that we had about exoplanets, really kind of redefined the way that we see exoplanets in the Milky Way and in the universe. It found nearly 2,400 confirmed exoplanets and had another few thousand exoplanet candidates that still need confirmation.
The little satellite that did, not just could, the little satellite that did, when they were planning the Kepler mission back in the late 90s, early 2000s, John Caldwell, one of the faculty members of the department here, was working on the field that Kepler was going to utilize, trying to ascertain basically the characteristics of the stars in that field and so on. And I remember John telling us that, they were hoping that they would find a few hundred exoplanets. That was the expectation. That was the hope, because, of course, we didn't know any of the statistics associated with planets' formation around distant stars. So everybody was very conservative, especially given the fact that, this was the transit technique. You've got to be in the plane of the planetary system, has to be in the plane of the sky that we're looking at of the star, and so on. A few hundred is what everybody was hoping for. And basically, they ended up with 10 times that many. So, yeah, it was a very ambitious mission, but it was a very exciting mission, and we're still working our way through the data furiously. It's going to take many more years to complete the follow-up observation. So definitely an exciting mission. As you say, TESS is the follow-up. There will be more missions looking for exoplanets, but Kepler blazed the trail, and it did it very, very well. Folks, you're listening to York Universe, the weekly broadcast of astronomy and astrophysics out of the Alan I. Carswell Observatory. Satish, Sana, myself, Paul, keeping you company this Monday evening for Astronomy Night in Canada. By all means, point your favorite web browser to observatory.info.yorku.ca and follow the links to OPV, online public viewing, and join the chat. Have a look at some of the wonderful archival images the observatory team is showing, because it's cloudy and we can't show you live images through our 1-meter telescope. But you have another chance later this week. On Wednesday, we have our Teletube, Telescope YouTube on, yes, you bet it, you got it, YouTube, 7:30 to 8:30 local time, so that's Eastern Standard Time. The observatory team will regale you with wonderful commentary and facts about some aspect of astronomy, and if it is clear, we will be able to show you live imagery through the 1-meter telescope. So that's this coming Wednesday, 7:30 to 8:30. So at the top of the hour, I asked both of you to prepare your answers for when did you decide you wanted to study astronomy? Sana, ladies first.
Well, I first got into physics when I was in high school because I thought it was cool. And then I came to this wonderful place now known as the Alan I. Carswell Observatory. And my interest kind of switched more towards astronomy at that point. So sometime around then.
So 4 years or so ago.
Approximately, yeah.
Give or take a bit. But you were interested in physics from the outset.
Mm-hmm.
Very good. Well, I'm glad we managed to turn you into the right pathway. Satish.
Well, I did have to prepare for this, and it's a simple answer. Probably it's been almost 30 years or more than that. And your question was, when did I decide, right?
Yes. So
yeah,
you were very young, in other words.
Very young. I'm actually not trying to say I was younger than 7, but it might have been the case. And I didn't watch any fiction movies back then, like science fiction. So
no Star Trek, huh?
Well, nothing of that sort, actually, because the first time I actually watched anything even remotely related to space was, I think, E.T., and that must have been somewhere around 1997 or 96, which was way after.
True.
I
I think
would have.
you mustn't have watched ET in its initial form, because I think ET came out a little earlier than that, but you probably picked it up on reruns. Very good.
Yes, I mean, it was yeah.
Very good. Okay, we've got only about 10 minutes or so to go. Should be enough to get through our two news items here. Sana, would you like to tell us a little bit about LOFAR and tell us what it is?
Sure. So LOFAR is the name of a array of radio telescopes based in the Netherlands. It stands for the Low Frequency Array. LOFAR is used for a couple sky surveys, and one of them is called the LOFAR 2-meter sky survey. They released last week a ton of data that was taken over about, I think it was 3,500 hours of observations, where they surveyed about a quarter of the northern sky using LOFAR at a wavelength of about 2 meters. So this is a massive project. It's part of an even bigger project where they want to use LOFAR to survey the entire northern part of the sky at an incredibly high resolution and sensitivity. They already released part one of this a few years ago in 2019, where they surveyed 424 square degrees of sky, finding about 300,000 objects detected at radio wavelengths. And then this new, the second data release that was released last week surveyed about 27% of the night sky. And the maps and the observations that it produced are crazy. It surveys the sky in an incredibly high resolution. Overall, it generated about 8 petabytes of data of the night sky, so just completely insane. It found about 4.4 million objects. Many of them are galaxies. Some of them are some kind of crazy stars in the Milky Way. Some of the galaxies are also normal, so galaxies with supermassive black holes or some starbursting galaxies, and also a couple rarer objects thrown into the mix too, like colliding galaxies. One of the really interesting things about this is that 4 million of the objects they detected have never really been observed using radio waves before, and then about 1 million have just never been found before. So they're completely newly detected objects discovered using this second data release of the survey. So this is going to be an incredibly useful data set used by a ton of people and can help study pretty much everything in astrophysics, from evolution of galaxies, evolution of black holes, physics of star formation, and can even be used to search for signals from nearby planets and nearby galaxies. So this is a pretty interesting and pretty exciting data release, and I am very interested to see articles in the coming months about, this sky survey discovered this and that. It should be very interesting.
Of course, you're most interested in the galaxies, but I understand that.
Yes.
It is certainly one of the big changes in astronomy over the last 10 or so years. It's these sky surveys. I recall, when I was going through grad school, forever ago, big sky surveys just did not exist, or there were so few and far between. But now, the richness of the data that is available to us, courtesy of these types of surveys, is just mind-blowing. And the amount of data that is coming down, I mean, you could drown in it. It's just phenomenal. But when you're trying to piece together, the patterns that exist in the universe, you need lots of data. You need good statistics, and that's what these surveys are able to provide. So, great stuff from LOFAR, and just one of many, many terrific sky surveys that are now available to up-and-coming astronomers like Sana and Satish.
Thank you, sir.
Satish, you want to talk a little bit about our return to the moon, so as to speak.
Sure. Okay, I hope I can fit this in. So the Kennedy Space Center, that's where everything happens, of course. And you've heard of the Space Launch System, which is a part of the Artemis mission. The Launchpad 39B will have a new visitor this month, and this would be a final launch rehearsal for the rocket system. So some news item somewhere even presents us with the time as 6 p.m. Eastern Standard Time. That is for this movement of giants that the rocket and the spacecraft are. The rocket itself perhaps weighs close to 17 million pounds, mounted on a 400 feet mobile launch tower. And this would be an 11-hour long trip to cover a mere 4 miles distance, or 7 kilometers, I think. So this will be followed by a couple of or more weeks of tests that I'm sure will be fun to watch. The launch window is between April 8th through April 23. That is for the Artemis 1 uncrewed mission. And they have two backup windows.
Yeah, that won't happen, just so you know. That window is not going to be met. Keep going. I'm just giving you a on-the-fly update. The April window will not be used.
Right. So they have two backup windows in May and June then. Maybe they'll just pick one of those. And this was supposed to happen in March, so that's probably the second dismissal that you just mentioned. And it got delayed due to the work needed on the system itself. So like I said, it would be an uncrewed mission. It is send the Orion spacecraft to fly around the moon in a multi-week journey. And the key idea is to demonstrate the system's efficacy at carrying astronauts, which will clear the way for Artemis to carry the 4 astronauts in the next few years, perhaps by 25. And just one bit of information, the SLS, or the Space Launch System, is powered by 4 RS-25 engines. That's the same workhorse which has flown the space shuttle over the past three decades and over 135 missions. It is capable of providing a thrust of 512,300 pounds in vacuum. So just wanted to throw that big number in there. Seems impressive. And that's actually approximately 10 times the thrust to weight power density of the strongest commercial jet available today, just to give you some perspective. So it'll be fun to watch.
We're all waiting for this dress rehearsal because that needs to be successfully completed to clear the way for the actual launch itself. And be it in May or be it in June, it will be exciting. Even though it's a completely uncrewed mission, it will be a return to the moon with a human-rated spacecraft. And we haven't done that since 1972. Okay, so we are 50 years since Eugene Cernan stepped off the moon, coming back to Earth. That was December of 72. And here we are with Artemis about to blaze that trail again. So, it's an exciting month for this process. It's a very slow journey, 11 hours out to the launch pad there. But if all goes well, we will be on the road to the moon again in May or June of this year. I, for one, can't wait. The Artemis 2 mission, which is a human-crewed fly around the moon, is at the moment expected in late 2023 or perhaps early 2024. There'll be a Canadian on board that mission. And if that goes well, then the real return to the lunar surface with people, boots on the ground, if you will, by the end of 2024 into 2025. It's a really exciting 3 years to come. So, fingers crossed for a very successful wet dress rehearsal this coming March. Folks, we're at the top of the hour. You've been listening to York Universe, the weekly broadcast of astronomy and astrophysics out of the Alan I. Carswell Observatory here in Toronto, Ontario, Canada. Sana, Shatish, myself, Paul, keeping you company this evening. Please stay tuned for the rest of the Science Night here in Canada, which includes the favorites of Western worlds, Science for the People, and a new presentation about mammals and marine science. We'll see you all again next week. Good night.
I hope that you've enjoyed this program.
Good night.
FM Radio, the broadcast service of astronomy.fm. This program has been released under Creative Commons license. Please contact us for details. You may find more of our AFM original programs on our website. It's really easy to find us. We are astronomy.fm. You may also find us in the iTunes radio listings near the top of the news